Hello, welcome back to our next lesson on conic sections. Today we're going to look at the fourth and final of the four conic sections, and this one is called the hyperbola. This one can be a little bit tricky to get the equation of or to graph, but it's very, very similar in some regards to an ellipse. The equation is set up much like an ellipse, but if you look at the graph, here's a picture of a graph. This begins on page 24 in your notes. And the first thing I'd like to point out is that you see this blue curve there and this blue curve over there. Well, that's an example of a hyperbola. There's actually two pieces to the hyperbola. And by the way, they don't have arrows drawn on the ends there. I wish they had. But these hyperbolas basically open up in, well, this one does, to the left and to the right forever and ever and ever, okay? Now, you might think that they kind of look like two parabolas that are back to back, but they're not parabolas. They're definitely not. Their shape is completely different from a parabola. A parabola, the two sides, the further you go to infinity, the two sides almost become parallel to each other. Well, not the case with a hyperbola. All right, so we're going to see how the hyperbolas are different from parabolas. The definition of a hyperbola is a set of points, coplanar again, they had to be in the same plane, such that the difference of the distances from two fixed points, and those fixed points are still called foci, just like they were for ellipses, but now instead of the sum of the distances being a constant, now it's the difference of the distances being a constant, all right? Okay, so let's look carefully at that. Let's look carefully at that graph that they have drawn there. I want you to notice, first of all, that this hyperbola opens to the left and to the right. All right, so that's what they look like, standard. That's one part of many, one form. But it's also quite possible that they could open upward and downward like this. All right, you can tell by looking at the equation, if you're careful, which direction they will open. It's either left and right, or they could open up and down. All right, so we'll see how the equations can tell you that if you look carefully at them. Now, in the center, right in between those two pieces, you have what we call the center of the hyperbola. And you get the center of the hyperbola from your equation just exactly like you did for ellipses or for circles. We'll see some examples of that. Okay, so that's your center. You're going to want to locate that. There are 2 points. Now, in this case, they're to the left and to the right. But you can see that your two pieces, your hyperbola, actually goes through those 2 points. And those are the vertices again. All right, so you have one vertex, in this case, to the left and right. But they could be up and down if your hyperbola is open up and down. And in your equation, that's still A. Okay, recall that for an ellipse, the distance from the center to either of the vertices was A, and it's the same thing here. This distance here is also A. Now, remember that for an ellipse, the line segment that joined your two vertices, we call that the major axis. Well, not so for a hyperbola. It's actually still a line segment, yes, and the length of it is still 2a, by the way, if you look carefully, but now it's called the transverse axis. The transverse axis is actually the line segment that joins your two vertices together. And the length of the transverse axis is 2 times a. All right. Notice that your hyperbola will pass through the two vertices. They do kind of act like the vertices of a parabola, don't they? It's either the point to the extreme left or right, or to the point at the extreme top or bottom. So in that regard, yeah, they kind of look like parabolas, but remember, they're not. So that's how you get your vertices. Now, there's also 2 points called covertices for a hyperbola. Now, they don't show them here in this diagram, but they're actually, one is up about there, and the other one is, in this case, down about there. They're the same distance from the transverse axes. So that's, I'll put CV there. There's one covertex, and there's the other covertex on the bottom. Now, they sort of form a line segment that's always perpendicular uh, to the transverse axes, and that line segment is actually called the conjugate axis. All right, the conjugate axis joins your two co-vertices together. The distance from the center to either co-vertex, well, ladies and gentlemen, that's still b. Okay, so in that regard, it's very similar to what we did for ellipses as well. And here, look at this. Here's one focus, and here's the other focus. Now notice this time, the foci are actually farther away from the center than your vertices are. That was not true for an ellipse, but it is definitely true for a hyperbola. Okay? So anyway, that distance from the center to the focus, by the way, is still c. Now it's kind of hard to see in this diagram because I've got it all cluttered up here now, but that's what we have. It's basically the same relationships for A, B, and C as there were for the ellipses. By the way, that conjugate axis, notice that one half is length of B, the other half has a length of B. So the length of the conjugate axis is 2B. It's the same thing as the length of the minor axis for an ellipse. So in that regard, the transverse axis is kind of like the major axis, and the conjugate axis is kind of like the minor axis, but that's not what we call them here. What else? Okay. Remember that for an ellipse, c squared was equal to a squared minus b squared. Well, it turns out that for a hyperbola, the relationship is almost the same, but now c squared is equal to a squared plus b squared. And that's how you calculate your c, or your c squared, from the equation. You're still going to see a squared and b squared in the equation, by the way. Okay. Let's have a look at what the equations look like. Now look at this. There's a few things I want to point out. First of all, let's look at this equation over here on the left. Now, how can I tell that that is going to be a hyperbola? Well, first of all, the x is squared and the y is squared. Okay, just like a circle, just like an ellipse. What else do we have? Oh, wait a minute. Look at that. You see that? See the difference? The x is squared and the y is squared, all right. But the terms are not added together. Actually, one term now is subtracted from the other. That's the key. That's how you tell a hyperbola from an ellipse. Now, you notice you have a squared and b squared again. It turns out that for a hyperbola, a squared is not necessarily the larger of the two numbers this time. So that's something you have to get in your head, something that's a little bit different. In this case, a squared is always under the positive term. Do you notice that? Look over in this equation to the right. There's your a squared. Notice that it's under the positive term, not the negative term. And it's not necessarily, a squared is not necessarily the larger number now. In fact, it's quite possible that a squared and b squared could even be the same number. But that doesn't mean it's a circle now. All right? And it's certainly not an ellipse. It's possible that a squared and b squared could be the same. The defining thing from your equation that tells you it's a hyperbola, look, is that sign right in the middle, that minus. And that's the difference. Notice they're both equal to 1, by the way. Okay, they're both equal to 1. All right. And what else should I point out about this graph? Okay, here's something else. Watch this carefully. Do you notice in the equation on the left, the x squared is your positive term? Well, if the x squared is positive, that means your hyperbola opens to the left and to the right, like that graph down there. Think of it this way. If the x squared is positive, then it will hit your x-axis somewhere. Okay, it will definitely intersect your x-axis. I just think that, I just keep that in mind. In the second equation, the second graph over on the right side, the y is positive, the y squared is positive, and that means, everybody, that it's going to open up and down. And I just sort of remind myself that really what that means is that it's going to hit the y-axis somewhere in two locations. It's going to hit it somewhere. All right? And there's something else I need to point out about these equations, and this is important for graphing. Do you notice that in the diagram, here's one vertex, here's the other vertex. All right, you can see that they're, in this case, to the left and to the right of the center. This point right here is supposed to be one of my co-vertices, and this point right here is supposed to be the other co-vertex. All right, now, One of the things you're going to be doing when you draw a graph is you're going to be plotting your two vertices and your two co-vertices. And when you do so, I want you to note that what they've done here is using the co-vertices and the vertices, they've actually drawn a box. Now it looks like a square here, but in most cases it's actually a rectangle. We are going to be drawing that rectangle every single time we have to draw the graph of a hyperbola. Notice in the diagram on the right, look, sure enough, there's now again, it usually is a rectangle or it could be a square, but you're going to get that box and you're going to be drawing it. And why do we need that box? Because you're going to use that box then, and you're actually going to draw, using a ruler, the two diagonals of that box. You see, there's one. Now, remember, a diagonal joins your corners together, right? Opposite corners. So that's going to be a big, long dashed line. You join the other opposite corners, and you get this big, long dashed line. And those are actually asymptotes. You see that word there, asymptotes? Well, asymptotes are lines that a curve gets closer and closer and closer and closer to, but never, ever, ever quite touches it, never, ever quite reaches it. Asymptotes occur in many places in mathematics. You're going to see asymptotes again before this course is over. So what really happens is if you look now at the graph on the left, is opening to the left and to the right, that black curve is actually getting closer and closer and closer and closer to that asymptote up above and closer down below. And the same thing on the left side. You see that? Closer and closer and closer and closer, but never ever quite reaching or ever touching that asymptote. In the graph on the right, the same thing is happening. They drew this box using the vertices and the co-vertices. They then constructed the two asymptotes. I'm going to be using dashed lines for the asymptotes as well. Now, the only thing is, because I'm using my computer screen, I won't be able to use a ruler. Not that I'm aware I can use a ruler anyway. So that would be one of the main constructions if you're trying to draw the graph of a hyperbola. Okay? And those two asymptotes, by the way, you could be asked to come up with the equations of those asymptotes. And in fact, if you go to the next page on the top, right there, do you see the asymptotes? Right there? The two parts of a hyperbola, the branches approach a set of asymptotes. An asymptote is a line that a curve approaches but does not actually touch. And here's what your asymptotes look like. Everyone, you see this? Now, I want to point out that the x minus h and the y minus k in both forms of the asymptotes, all right, you get those directly from your equation, whatever your equation is. So let me go back to the equations. Whatever this x minus h is, whatever this y minus k is, it's exactly the same for your asymptotes. But notice that for the asymptotes, they're not squared. Because remember, asymptotes are lines. If either one of those terms there was squared, you would not have a line, would you? And the only thing you have to kind of think about, the only thing that could be tricky is not getting the x minus h and the y minus k. That's easy. But it's this part. You see that? These are what we call the slopes of your two asymptotes. If the hyperbola opens left and right, like this one does, then notice that the asymptotes are plus and minus b over a. Now remember, you get your b and your a from your equation. A squared is always under the positive term. B squared is always under the negative term. If your hyperbola opens up and down, then your two asymptotes, the slopes, are positive and negative a over b. Okay, so you have to basically remember, you have to know what they are. But I'm going to tell you the way I remember it. Come back to your equations up here. Let me just get rid of some of this clutter. Now I want to show you something. If I'm coming up with the asymptotes, the slopes of the two asymptotes, because the x minus h and the y minus k, that's easy. But it's the slopes of the asymptotes that can be tricky. Now, watch what I'm going to put over here. The slopes of the two asymptotes, if your equation looks like this, if it opens to the left and to the right, and remember now, these are the asymptotes, then the slopes are equal to, now you know it's always plus and minus, because one is going up to the left and the other is going up to the right always. Look at what's under your y squared right here. Okay? Now notice that if the x squared is positive, that means the y squared term is negative, but it's the b squared under the y squared. Well, it turns out that whichever one of those two letters is under the y, that's what goes in the numerator of your slope. So in this case, I see that, okay, the b squared is under the y squared. So this one starts out b over a. There's my slopes. And the x minus h and the y minus k is easy. Come over to the one on the right. All right, the asymptote slopes is equal to plus and minus. I mean, you think about this. You can get the slopes of the asymptotes without doing one single calculation. Nothing. No calculation is required. Now, again, here's the y squared term. Look at what's under the y squared. It's the a this time, isn't it? The a squared is under the y squared. So that's what goes on the top in my slopes. Now, that's the way I remember it. That's the way I remember it. If you want to think up some little trick on your own to do it somewhat differently, you go right ahead. But that's the way I remember how to get the slopes of the two asymptotes. Now that's a lot, isn't it? There's a lot there to digest. I'm just going to do a couple of examples here. I think the last video I made on the ellipses, I'm going to try to make these shorter. I think that like the last video might have been a bit long, I think. And so there's, okay, yes, there's one other thing right here on the bottom of page 25. Now, we don't do a whole lot with this, but there's another form that the equation of a hyperbola can take on. Basically, just something like that right there. You see that? X multiplied by y equals a constant. That will also give you hyperbolas. But you notice they don't open up and down or left and right. These kinds of hyperbolas actually open diagonally on either a diagonal up, up to the right and down to the left, or vice versa. All right. So the equation for this one could be something like x times y equals just 4. X times y equals 4. The equation of the one on the right could be something like x times y equals negative 4. All right. Now, how do I tell the difference? Well, because in this one, the signs of the x and the y will be the same, so obviously x times y will be a positive value. But over here, the signs of your x and y, any point on that curve, you see, one is positive, one is negative, aren't they, the coordinates? And therefore, if you multiply them together, you get a negative. So you're not going to be graphing those or anything. Basically, just recognize that that's a hyperbola, kind of a simplified version of a hyperbola. Okay, so we're going to do examples on page 26, number 1 and 2, and that's all I'm going to do in this video, and then I'll give you some practice to work on. I'll actually make up a second video, okay, on this, because I don't want to throw too much at you. Like, this is not trivial stuff. You have to kind of digest this before you can actually get it. So let's see what number 1 says. It says, for the hyperbola x squared over 16 minus y squared over 9 equals 1, state the center, the foci, the vertices, and I'm going to include the co-vertices as well, by the way. So we have to get the center, the foci, the vertices, also the co-vertices. You're going to need it anyway. You're going to need it anyway because this actually says sketch the hyperbola. They want you to draw an accurate diagram or an accurate graph. And also the equations of the asymptotes. Now I'll tell you one thing. Remember what I just said a moment ago about the asymptotes? Look at this carefully. I can get the slopes of those asymptotes right now without doing one single calculation. You watch this. The slopes are going to be plus and minus. Now look at what's under the y and look at what's under the x. Now remember, that's a squared and b squared though. You have to take their square roots. I should have mentioned that in the previous page. But under the y, you have your 9. Well, the square root of that number is what goes on in the numerator. So it's 3. And look at the other one that's under the x. Well, that's 16. The square root of that number is 4, and that's in the denominator. And there you go. There's the slopes of your asymptotes. It's that simple. I could get that. In fact, that would be that would make an excellent multiple choice question, right? Because it's very short and very sweet. Now, okay, let me go. I'm going to actually write this or draw this, put the equation down below because I'm going to need to move down. X squared over 16 minus y squared over 9 equals 1. Now, notice, first of all, I can clearly tell that's a hyperbola. I can clearly tell that because the x is squared, the y is squared, and there's a subtraction sign in between them. All right, the signs of them are different, to put it that way. So that's definitely a hyperbola. Now, I wish I'd made that a little... Okay, just remember, that's... Tell you what, I'm going to bring those squared sides down a little bit further. So that's squared, squared, and now I think I can move it up a little more. There you go. Okay, so let's look at this hyperbola. Now remember, the a squared is not necessarily the larger of the two. In this case, the a squared is under the positive term. So it is 16, yes, but not because it's the bigger number. A squared is 16 because it's under the positive term. So in this case, a is 4. There's your a. And what else do we have? Let me see. The b squared is the number under the negative term behind the minus sign. So b squared here is 9. That tells me b is 3. Now those are important numbers because, do you know what? That tells me how far up, down, left, right to go from my center. Oh, and by the way, guess where the center is in this case? The center is at, well, what's subtracted behind the x or the y, or added or subtracted behind them? Nothing and nothing. So there's your center. And also, do you notice that the x is the squared term here, meaning that this hyperbola has to hit the x-axis somewhere. It might not hit the y. Well, if that's the case, it's got to open left and right, you see? Now that's important. That's really, really, really important information. So let me see. I've got my center. Here's my center right there at 0, 0. And because it opens left and right, that means that my two vertices will be a units left and right from that 0, 0. So if I go 4 to the right, there's one vertex right there. If I go 4 to the left, there's my other vertex right there, because this hyperbola opens to the left and to the right. So actually, I can even write those down here now. Vertices are negative 4 and 0, right? And the other one is positive 4 and 0. There's my two vertices. There's my two vertices right there. And your co-vertices, you want to get those next? Watch this. The two co-vertices are, now in this case, again, because it opens left and right, the co-vertices actually, they don't really intersect anything. Like one is above and one is below the transverse axis. That transverse axis you can look at right there now, everybody. That's 8 units long, isn't it? Well, the co-vertices are up and down from the center. That would be your conjugate axes, and that's perpendicular to your transverse axes. But anyway, look at that. My b is 3. So I just go 3 up to there. There's one co-vertex. And I go 3 down. 1, 2, 3. And look at that. There's the other co-vertex. See that? And it looks like a square. It's going to form a square, but it's not. It's really a rectangle. Okay, so let me see. Now, isn't this simple? Having that piece of graph paper there and knowing which way to move makes this actually pretty straightforward. So my two co-vertices, one is at 0 and negative 3. All right, that would be the one that I moved down to. And the other one is at 0 and positive 3. And that's the one I kind of had to move up to. Now remember, if this if this hyperbola had opened up and down instead, then I would have had to go up and down from my center to get my vertices, and I would have had to go left and right from my center to get my co-vertices. Now, look at that. Do you know what, everybody? You can graph that right now. You could make a very, very accurate drawing of that hyperbola now without doing a single calculation more. Because watch what we're going to do. You are going to use the vertices and the co-vertices, and there 4 of them are there. You're going to draw a box, a rectangle. And your rectangle is going to be as wide and as high as those 4 points are. All right, so watch what I do. Now I'm going to try to show it clearly what I'm doing here. So You see that? I'm making a dashed line. Okay, down that far, and then I'm going to draw my dashed line over here. Okay, and once you got your vertices and your co-vertices, this is easy. And it's got to be as high as the co-vertices are apart. Now look at that. Now it wasn't that simple. I just made a box. Now, I wish I had a ruler. I wish I could use a ruler on this. I don't think I can. I haven't figured that part out yet. But now you take a ruler, a straight edge of some sort. I'll be looking for that on a test or a quiz. And you draw nice long lines right through opposite corners. That would be the two diagonals. So one is going to look something like this. Let me see if I can try to draw these a bit straight. Now, like I'm just roughing it here now because I don't have a ruler, but you use a ruler. Now there's one, and then this way, something like that. There you go. There's one of my asymptotes. There's one of the asymptotes. And the other one joins corners like this. And again, I wish I had a ruler because it would be really, really neat. You use a ruler, remember. Now look, there's your asymptotes. So you're going to draw curves now, opening left and right, remember, going through the vertices. You have to make them go through the vertices. And their curves, the edges, the sides are going to get closer and closer and closer to those lines right there. And I mean, you're doing it freehand. So one side would look something like that. All right, getting closer and closer to that line. The other side down here is going to look something like this. Again, I'm showing it getting closer and closer to that dashed line, that asymptote. And over on the left side, I do the same thing. Look at that. There's one side, something like that. And the other side is something like that. Now, wasn't that easy? It is. Really, as soon as you know where your vertices and your co-vertices are located, you can draw that hyperbola. Now, I'm still missing something, though. I haven't put my foci in, right? And I also haven't found the equations of the asymptotes either. So let me get my foci. Now, that would involve the c squared. Now, remember, though, for a hyperbola, c squared is a squared plus b squared. You might end up with radicals here when you take the square root of c squared. You might end up with a radical, and that's fine if you do. Or you could change it into a decimal. Now, you know your foci are farther away, from the center than the vertices are. So one foci is going to end up over here somewhere in this region, and the other foci is going to end up over here somewhere in this region. Now, they might be close to the vertices. Yes, they could be very close, or they could be kind of far apart. But that's about where they're going to end up. So let me see, a squared plus b squared. Well, a squared was the 16 in this case. B squared is the 9. Oh, you're going to get a nice whole number. Look at that. Now, that doesn't happen all the time. All right, so c is equal to 5. All right, c squared is 25. Take the square root, you get c equals 5. So 5 to the left and 5 to the right from the center. So there's one focus. All right, right there. And the other focus, 5 to the right, is right there. You should put in your two foci when you're graphing a hyperbola. Yes, you should put in your two foci. That's vital. That's important. Okay. All right, what have we not done yet? I found the vertices, I found the center, I found the foci, I even found the co-vertices. The question never asked for that, but I had to get the co-vertices anyway in order to draw that box to get my two asymptotes. Oh, they're asking for the equations of the asymptotes. All right, well, watch this. Let me just clear up a little bit of space there so I can write that down. I'll just clear this out of the way, and I'll just clear this out of the way, and I'll clear this out of the way. All right, so I want my asymptotes. Now, remember, the center was at 0, 0. So that means instead of y minus k equals, you're just going to have y equals. And on the other side, the right side, instead of having x minus h, well, you just got x. Your two slopes, don't forget your plus or minus. You can see one's plus and one's minus. Actually, you can look at that graph and tell what they are anyway, what your two slopes are. Now, what's under the y? Well, the 9 is under the y. Look at that. So the square root of that number goes on the top. That's 3. What's under the x? 16. The square root of that number goes on the bottom. And there's your asymptotes. Ta-da! That's all there was to that. They're done. Okay, so that one was actually pretty straightforward. That one wasn't too difficult at all. We got everything done. We Yeah, the graph looks pretty good. If I had a ruler, it would look even better. All of these solutions, all of these graphs are drawn on D2L. Make sure you look at that very carefully. Now, there's another example here, number 2. I think what I'll probably do is leave that one to do in class, along with some of the other examples that are there. Now, what can I tell immediately from this hyperbola just by looking at it? Well, I can tell this time it's going to open up and down, because the y squared is positive this time, so it's definitely going to open up or down. What else can I tell? I can tell that the slopes of my asymptotes are going to be, well, what's under the y? It's a 4, so the square root of that is 2. What's under the x? It's a 3, or 9. The square root of that is 3. So the slopes of the asymptotes is going to be plus and minus 2 over 3. Look at that. Now, how much work did that take me? Nothing. The center is at negative 4. Okay, so the center is at negative 4, because look at what's behind the x plus 4, and then look at what's behind the y minus 2, so that's positive 2. There's your center, look at that. So negative 4 and positive 2, boom, center already. Now, wasn't that easy? The a squared is under the positive term. There's your a squared. It's not 9, it's 4. So a is equal to 2. All right, and because I know that my hyperbola opens up and down, to get my vertices, that's my A, right, from the center to the vertices, I go up and down 2. So look, boom, there's one vertex right there, and I go down 2, and boom, there's the other vertex. Now, wasn't that simple? That was easy. And watch this for the b squared. B squared is the number under the negative term. So in this case, it's 9, so b is equal to 3. I'm just going to show you really quickly now how easy it would be to graph this. And remember, the b is the distance from my center to my co-vertices. Now, in this case, it's left and right. So I go 3 to the right, and I go 3 to the left. Now, remember, you can write down these coordinates as you're plotting these points. It's very, very simple. But there's one co-vertex, and there's the other co-vertex. And like we did in the last example, people, you can graph this right now. You can make a perfectly accurate graph by drawing your box. Remember, you draw the box like so. It's so simple. There's the box. All right, you draw your diagonal, so one will look something like that. Again, I'm just roughing this now. Remember, you're using a ruler. And the other one goes through the other corner, so something like that. And now, you know it's opening up and down. It must pass through the vertices. So look, there's one side, and there's the other side. Now, wasn't that simple? How long did it take me to draw this graph? Not very long. There's the other side. Now, there's what your graph looks like. Now, yes, you have to get your foci in there as well. Don't forget to get your foci. Your c squared equals a squared plus b squared. But I'll leave that one for you to try, okay? So you finish that one, and also the examples that are on page 27. I don't want this video to go on as long as the last one. These examples right here, for each hyperbola, determine the coordinates of the center, okay, the vertices, the foci, the direction of opening, and the equations of the asymptotes. I noticed that none of these ask for the co-vertices, but really you need to put those in. Please make sure you write down the coordinates of the co-vertices as well. So you can do A and B and C. None of those look tricky at all, okay? And anyway, I'll stop there. So you try those practice ones, and when we come back for our next lesson, we'll start with example 2 on page 28, but everyone, we've done those now. Sketch hyperbolas, drawing hyperbolas. I'll do one of those examples anyway, probably number 1, and I'll do number 3 as well, because in number 3, they're not quite giving you the equation, are they? They're actually giving you some information, but we'll do number 3, and we'll also do number 4. And by the way, there's a mistake in number 4 in the way they've asked the question. Number 5, I'll tell you what, I might leave number 5 for in class, but that one is nasty. That one is really, really tricky. I don't know if I'd ask one like that on a test or not. We will look at it maybe, but maybe not. Now back to number 4 on the top of page 29. I want you to make a change. The vertex at 0, -1 is okay. This focus is wrong, okay? And the reason it's wrong is because if you were to graph this the way it looks, you'd actually have the foci closer to the center than the vertices are, and that's not supposed to happen for a hyperbola. So I want you to change the focus, cross that out. I want you to put one of your foci at 0, 6. So you make that change, and now you can do question number 4 on the top of page 29. Well, actually, that's after our next lesson anyway. But you just try the ones on page 27, okay? And I'll stop there. Bye-bye for now.